All right, guys. Where we got to yesterday was this here, finding all the rational zeros, our plus or minus p over q. Do we want to look at 25 or 26?
26.
Okay. 26 for the possible rational zeros is our plus or minus p over q, where p is the factors of the constant term.
Attention and attention, please. I need the following students to report to routine. Brent Gifford, Lauren Hickok, Addison Jinks, Destiny Jones, Sean McFerrin, Melanie Yang, and Charlie.
So p is the factors of the constant term. Our constant term for this here is 15, the one without a variable. So the factors of 15 are 1 and 15, and 3 and 5. So factors of p, factors of the constant term, are the factors of the term without a variable. Q is the factors of the leading coefficient. Leading coefficient is the number in front of the variable with the biggest exponent. This case is 12. So we'd have 1 and 12, 2 and 6, 3 and 4. Q is the factors of the leading coefficient. P is factors of 15, yes. Q is factors of 12. And now to find all the possible rational zeros is we're going to take every factor of P and divide it by every factor of Q. And to do this, I normally do it one factor of Q at a time. So the first thing we're going to do is divide 1, 3, 5, and 15 by 1, or put it over 1. And we will have plus or minus with each one of these here. So we'd have 1 over 1, which is 1. Plus or minus 3 over 1, which is 3. Plus or minus 5 over 1, which is 5. Plus or minus 15 over 1, which is 15. And now we're going to repeat the process, but this time with Q being 2. So we'd have plus or minus 1 over 2. Then we'd have plus or minus 3 over 2. Plus or minus 5 over 2. And lastly, plus or minus 15 over 2. Now, at any point along this process, we have a set that can simplify or reduce. We need to reduce them. But 1 over 2, 3 over 2, 5 over 2, and 15 over 2, none of those reduce. There's not something in common that would reduce. Now, if we look at the next one, 3, we'd have plus or minus 1 over 3. The next one after that is 3. Does 3 over 3 reduce? Or just 1? Is it already listed? If it's listed, we don't have to repeat it, so we can move on. 5 over 3, does that reduce? No, so we'd have plus or minus 5 over 3. And then the last one, 15 over 3, does reduce to 5. 5 is already listed, so we don't have to do it again. Then we'll move on to 4. So we'd have 1 over 4. Doesn't reduce. The next one would be 3 over 4. Does it reduce? No. So we have plus or minus 3/4. The next one would be 5 over 4. And then lastly would be 15 over 4. Now, part of the reason we didn't have to reduce or list all the ones with 3 is because 3 and 15 had a common factor of 3 with 3, so they reduced and we didn't have to list them out. However, 4 does not have a common factor with 3, 5, or 15, so we had them all. The next one we're going to do is with 6, so we'd say plus or minus 1 over 6. It doesn't reduce. The next one, 3 over 6, does it reduce? Because again, we could plug all these into the calculator and see if they reduce. And the next 3 over 6 reduces to 1/2. 5 over 6 does not reduce. And yes, the 1/2 is listed, so we don't have to write it again. 5 over 6 doesn't reduce, so we list it again. 15 over 6. Again, we can keep plugging these. Not that. 15. Well, that's y is 5/2. And we already have it. So, and that's the last one for it there. So we move on to 12. So the first one we would do is 1 over 12. It doesn't reduce to anything more than 1/12. 3 twelfths, will it reduce? Well, yes, to 1/4. We already have it. 5 twelfths, does that reduce? 15 twelfths would reduce to 5/4, and we have it. So these here are all of our rational zeros. That's it. Because all it's asking is to find the rational zeros. It does not say to solve. Even if we did try to solve, none of these zeros work. Questions on 25 and 26? And you do need to include the plus or minus. Yep. I do assign points for both the positive and negative case. So if you don't put the plus and minus, that is half the answers.
So, list another one. You know, catch it, list it. Can we list anything?
If you list a number twice, there's nothing wrong with that because it's just repeated. So I'm not too concerned with repeated ones. It's unnecessary ones we'll start looking into. Because if you put 13 in this, that's not right. Because 13 is not a factor of either one. Does that make sense? Okay. Any other questions? We good with this here? 27 or 28 with Descartes' rule of signs to find the number or the possible number of positive, negative, and complex solutions. Which one do we want to look at? (28). Now the degree is what? 7. So that tells us the number of solutions we should have is 7. So when we get everything said and done, there should be 7 total of our positive, negative, and complex of any combination. Now, to find the number of possible positive zeros, we take the starting function and count the number of sign changes. So looking at this here, x to the 7th, x to the 5th, it's going from positive to, so that's 1. The next one goes from negative to positive. That's 2. Then we go from positive to negative, which is 3. Then we go from negative to negative, so that does not count. And then we go from negative to positive, which is, and the last one we go from positive to negative, which is 5. So the number of positive solutions we can have is 5 or an even amount less than that. So we can have 5 or 3 or 1. Because to find all the possible choices, we just keep subtracting 2 from the most that we could have until we hit 0, or it's going to make it negative. So
we subtracted 2.
So we subtracted 2 from 5 and got 3. We subtracted 2 again and got 1. If I subtract 2 again, it would be what? Negative. We can't have a negative amount of positive solutions. So these are our 3 choices. because for any of these here, whatever we get, number of sign changes minus an even amount. Now, a negative case, we're looking at g of negative x. And the biggest thing for this here, finding this, if the exponent's odd, we change the sign. If the exponent's even, we leave it. Because we have to do this to be able to find it, the number of negatives. So if we look at the first term, it's 6x to the 7th. Is the exponent even or odd? So what's our exponent? Exponent here.
Wait, what?
What's the number of the exponent? Is that even or odd?
Wait, what? Oh! I was thinking it was negative or positive, sorry.
So the exponent's 7, which is, you got it this time, odd. If the exponent's odd, you change the sign. It was positive, which means it's now negative. The next one is 5x to the 5th. Is the exponent even or odd? Odd, so we change the sign. It was negative, it's now positive. Let's look at the next term. 27x to the 4th. Is the 4th power even or odd? So it stays the same. Since it was positive, it is still positive. Our next one is 30x cubed. Is the exponent even or odd? 3 is odd, so our sign is going to go from negative to positive. Our next term is 20x squared. Our power is 2. Is that even or odd? Even, so the sign stays the same. It was negative, it's still negative. Our next term is 5x. Even though we don't write it, the exponent for this is what? 1. 1 is odd, so we change the sign from positive to negative. We can't do anything to the number without a variable because it does not have a variable. Questions on how we got to this here? So for Descartes' rule of signs, when we're trying to find the negatives, when we rewrite it out, if the exponent's odd, change the sign. If the exponent's even, keep it. Keep the same sign. Let's count the sign changes. For our first one, we're going from negative 2, so that's 1. The next one is positive to positive, so no. Next one's positive to positive, so no. Our next one, we're going from positive 2, so that's 2. Now we're going from negative to negative, so no. And lastly, negative to negative, no. So the number of possible negative solutions is 2, or less than it by an even amount. So we could say 2 or 0 because we keep subtracting 2 from it. But if I subtract 2 from 0, we get a negative, so we're done. Questions on this here? Because it's the number of sign changes or less than it by an even amount. Now, really what we're doing next is arranging these in every possible combination. Every way we can connect the 5, 3, and 1 with 2 and 0. Now, I think and believe the easiest way to do this is start off with the most positives and most negatives we can have. So the most positives we can have is 5. The most negatives we have is 2. And really what we're going to end up doing is just connecting every positives with every negative. Because we can have 5 positives and 2 negatives. It's one combination. Now the total of solutions, the total that this should always equal coming across is the same as the degree, which is 5 plus 2 is, so how many are we missing? None, so there are 0 complex. We have all 7 solutions. Now what I normally do is I just subtract 2 from our negatives, because again we said we can have that number of negatives or less than it by an even amount, less than it by 2. So I can take 2 away from our negatives and get 0, because that's our other choice. So we can have 5 positive solutions and 0 negatives, which gives me a total of 5. We're missing 2, so there are 2 complex, because again we said how many solutions should we have? 7. So if I have 5 positives and 0 negatives, I have only 5 solutions, which means the other 2 have to be complex. Can we take 2 away from our 0 for the negative? No. So what we do, and what I do, is I reset it back to its highest amount.
Wait, so how do we get the negative? Oh, the sign change.
Yep. And I take 1 away from the positive. So now we're going to look at every possible combination of 3 positives and all of our negative choices.
Okay, so will we do that for, even if it goes from a negative to a positive or positive to negative, it's still.
That's how many times they change. Yep. Now here, at this point, we have 3 positives and 2 negatives, which gives me how many solutions total so far? 5. How many do we need total? 7. So how many are we missing? 2. Because 7 minus 5 is 2. We have 2 missing, so we have 2 complex. And we repeat this process because we can take 2 away from our negatives, which tells me I could have 3 positives and 0 negatives, which is a total of how many solutions? How many are we supposed to have? So there would be 4 complex. Because again, if you need or want to, we can always add one more column, which is total, and just coming across the top. 5 plus 2 plus 0 is 7. 5 plus 0 plus 2 on the next one is 7. 3 plus 2 plus 2 is 7. 3 plus 0 plus 4 is 7. Because our total should always be 7, because that's the degree, the number of solutions. Can we take 2 away from 0? Can I take 2 away from our 3 for the positive, which is 1? I reset the negatives, because I could have 1 positive and 2 negatives, which is a total of how many? 3. How many are we missing? 4, which gives us a total of 7. Now, we can subtract 2 from the negatives, which means our last combination is 1 positive, 0 negatives, and how many complex? 6, because again, it needs to equal 7. The total list, that total column we added, you don't need it. It's not necessary for the test. I do want everything in green. So all of this here is the answer choices. Now the reason we can say we're done is, well, I can't take 2 away from 0 anymore. And we can't take 2 away from 1 anymore. So we're finished. Those are all the possible arrangements. Yeah, and really all we're doing is, these are our 2 arrangements here. And then we have here, every way that I can combine the possible positive solutions, so 5, 3, and 1, with our positive negatives, 2 and 0, and we're listing them out. And this here is how I've found to be the easiest to do it, is I take 2 away from the negatives, so I can't do it once with the positives, and then repeat the process over and over again.
So we'll never take anything over from C.
Now C, our complex, is what is missing. Because the degree is 7, so it should always add up to 7. If it doesn't, whatever is missing from that amount is what's going to be complex. They kind of fill in the gap for what is missing from our total number of solutions. And the complex will always be an even amount. 0, 2, 4, 6, 8, 10, 12. Because as we said with complex solutions, they always come in pairs. They're always coming in pairs of 2, A plus BI and A minus BI. If we have one, we have to have the other. So that means if they come in pairs, there's no way we can have 1, 3, 5, 7 for the complex. (29 through 34), solve. Which one of these do we want to look at? (29). Looking at problem number 29, what is the degree of this problem? So how many solutions should we have? The first thing I would do with any of these here is graph it. Because if we graph it and find 5 solutions, we are done. Because if we find 5, we've found them all and we are finished. But on every problem on the test, for this here, the graphing calculator will always give you at least 2 less than whatever the degree is. So here the degree is 5. Well, what's 2 less than 5? 3. So the graphing calculator will give you at least 3 solutions. It could give you 4. It could give you all 5. It will never give you less than 3 for a degree 5. And if we graph this, we get this here. And as it's set up with this here, and I can reset it if you need on the test, the x values that this graph will show is between -10 and 10. We see that it crosses the x-axis in 3 places, yes? So that means that there are 3 solutions that we see here between -10 and 10. Now it does look like every single one crosses at a nice point. So we can go second graph. And we do find 3 values for x, which make the y value 0. And they are 1, 4, and -5. And that does give us enough to start with, because again, we need 5, and we can use these 3 with synthetic division to get it from a degree 5 down to a degree 2. We need 3 solutions to get it from a 5th degree polynomial function down to a quadratic. Now our numbers going across the top, we'd have 1 for x to the 5th. Do we have an x to the 4th term? So it's 0. We'd have -20 for x to the 3rd. 20 for x squared, -21 for x, and 20. We'll bring the first term down. Which x do we want to use first, 1, 4, or -5? 1. And we'll do our synthetic division process. 1 times 1 is 0 plus 1 is 1 times 1 is -20 plus 1 is -19. 1 times -19 is -19. 20 plus -19 is 1. 1 times 1 is -20 plus 1 is -20. 1 times -20 is -20. And 0 plus, or not 0, 20 plus -20 is 0. Now again, found it. Second graph. So
What is this?
someone had it in English standard form instead of just
So it was 1,
for -5. Which number do we want to try next? 4. And we'll repeat this process again. 4 times 1 is 4. 1 plus 4 is 5. 4 times 5 is negative 19 plus 20 is 1. 4 times 1 is 4 plus 1 is 4 times 5 is, and negative 20 plus 20 is 0. And when doing this here with solving, we should always expect the remainder to be 0 because each one of these is a solution. And if it is a solution, if it is a factor, the remainder is 0. And the last one we can do is negative 5. Negative 5 times 1 is 5 plus negative 5 is 0. Negative 5 times 0 is 1 plus 0 is, and negative 5 times 1 is, and 5 plus negative 5 is 0. Questions on this here? So the last thing we have plug the variables back in. The number in the box is our remainder. The number next to it, 1, is our term without x, our constant term. Our 0 is our term with x, and the other 1 is our term with x squared. Now we can do this by the quadratic formula. And again, it might be helpful to have that down. But since we don't have a middle term, we're going to get x squared by itself, so we'll subtract 1 from both sides, telling us x squared is equal to negative 1. Then at this point here, we would square root both sides. The square root of x squared is x. Anytime we take the square root of both sides, we add the plus or minus. And we're going to take the square root of negative 1. 1i or just I. Because the I is by definition the square root of negative 1. So the square root of negative 1 is I. The which one? The 30xs? The yellow calculator? The TI-84. Up at the top, if it says a plus bi, it will take the square root of a negative. Square root of negative 1 is I. Now we do need to be careful because if we take the square root of negative 2, can we take the square root of 2? So up the top, because we have normal, float, auto. The next one, does it say a plus bi or real? Or it doesn't, probably doesn't say it at all. Hit mode. Halfway down the screen, does it a plus bi, is it in bold or in a black box?
It says real and then
So if real is the one that has the box around it, you need to scroll down and go over to a plus bi and hit enter. And then second quit and try it again. Now, if it was something like the square root of negative 2, the square root of 2 does not reduce nicely. So it gives us that as a decimal. And for all the ones we're going to do, and especially on the test, I do not want it in decimal form. I want it in radical form. So for like the square root of 2, the negative would come out as I squared root of 2. The yellow calculator can do the radical, but you have to get rid of the negative first. So we'd pull the negative out as I, and then go from there. So all, because the other three solutions that we had were negative 5, 1, and 4. Yep. You can list them out at the bottom or list them out at the top. I just need them all listed somewhere. Because our positive and negative I is 2 solutions, and then we had the 3 we had already.
We could just do x plus or minus I, just circle this.
Mm-hmm. Yep, as long as it is apparent where your solutions are. Any other questions on 29? 30 through 34, is there another one of these that we want to look at? Which one? 32. Is there a constant term? 0, there's not one. If there's not a constant term, it's understood that one of the solutions for this is going to be 0. So here it is 0. One other thing that's interesting is whatever the smallest exponent attached to a variable is, will actually tell us the number of zeros that are 0 for this solution. Well, the smallest exponent is what? So 0 actually appears. And it's kind of easy to prove. Synthetic division, because we're going to do 0 first. 9 for m to the 5th, 0 for m to the 4th, negative 27 for m cubed, 0 for m squared, 0 for m, and 0 for our constant. Bring the 9 down. I said this earlier today, and I'll say it again. The only thing that I think y'all like better doing with multiplication than multiplying by 1 is multiplying by 0. And I think that's been true since elementary, yes? 0 times 9 is 0 plus 0. 0 times 0. Negative 27 plus 0. 0 times negative 27 is 0 plus 0. 0 times 0 is 0 plus 0 is 0. 0 times 0 is 0, and 0 plus 0 is 0. We got a remainder of 0. Well, so that means it is a solution. We can do this again. 0 times 9 is 0. 0 plus 0 is 0. 0 times 0. Negative 27 plus 0 is negative 27. 0 times negative 27 is 0 plus 0 is 0 times 0 is 0, and 0 plus 0 is. So again, we got a remainder of, so it's worked twice. Let's try it once more. 0 times 9 is 0 plus 0. 0 times 0. Negative 27 plus 0 is 0 times negative 27 is 0, and 0 plus 0 is. Negative 27 is our constant. So if we tried 0 again, it wouldn't work. Because just like all the previous ones, we keep getting 0. And we would need a 0 at the end to finish this. But we get to this point here. Now we do have a quadratic. Well, have we actually graphed this thing at this point? No. So at this point, we knew 0 was going to be one of the solutions because, well, constant term, there is not one. So it kind of led us to this here. So instead of trying to plug the original one in, let's plug what we have. Because this is the remainder, negative 27 is the constant, x squared. So really what we have at the moment is, yeah, 9x squared minus 27 plus negative 27 is the same thing. But we can graph it. Because again, those are the two solutions we are looking for. Because I mean, our original function was 9x to the 5th minus 27x to the third, yes?
So negative, just negative 27.
So,
You're on negative.
because we have these three spots here, the red and the blue, if you notice the only difference between them is that it crosses at 0. It does cross at our two other spots, but 0 is the one that's added. This? Yeah, because I also added our original one in to show that it does have almost the same thing, our two solutions that we have left. We just removed the 0. The spots where it's at 0 for the original one. So even if I did check the graph, it does not cross at a nice point. So we just need to solve this quadratic. No middle term. So we can add 27 to both sides. Telling us 9x squared is equal to. At this point here, we can. We're going to divide first. Because our 9x squared divided by 9 is x squared. 27 divided by 9 is 3. And lastly, we need to square root both sides. X is equal to plus or minus, because whenever we take the square root of both sides, we have to add the plus or minus. What's the square root of 3?
In this case, they would be what?
Yep. Because again, we're trying to find what number times itself is 3. What's the next perfect square after 3? 4, yes? Well, what's the square root of 4? 2. So whatever the square root of 3 is, it would be close to 2. It wouldn't be over it, but it would be close to it. That's why we get 1.7. But we also found the other three solutions as 0, 0, and 0. Questions on this here? Is there another one we want to look at? We're good with all this here. Now with any of these, especially with solving, as we saw with 29, even if we just graph it, and we don't know what to do after that, we will get at least 3 out of the 5 solutions. It does give you a place to start. Are there any other questions? All right.